This video is the third and final part of our discussion on the rigid rotor model. As mentioned in the previous two videos, the rigid rotor is the third of the fundamental model systems we study in quantum chemistry. Again, the first is the particle in a box, the second's the harmonic oscillator, and again, the third and final model system we'll look at is the rigid rotor. So we've done this in three parts. We studied the classical rigid rotor model, we've treated the rigid rotor quantum mechanically, and now in this video we're going to focus on using the rigid rotor model to understand rotational or microwave spectroscopy, in particular for diatomic molecules. The learning objectives of this video are twofold. First, we want to be able to relate the results of our quantum mechanical treatment of the rigid rotor model to the sorts of terms that are conveniently used in rotational spectroscopy. And second, we want to use spectroscopic data to determine the reduced mass or the bond length and other parameters of diatomic molecules. In our last video on the quantum mechanical treatment of the rigid rotor, we saw that the rigid rotor serves as a good model for understanding the quantum mechanical behavior of rotating systems. We wrote down a Hamiltonian that involves the total angular momentum squared operator, and as shown on the right, h is equal to L squared on 2I, where I is the moment of inertia. The rigid rotor energies are quantized, and we introduced a new quantum number j, which is equal to an integer greater than or equal to 0. And lastly, we pointed out that rigid rotor eigenfunctions exhibit degeneracy, and the degeneracy g sub j, as shown on the right again, is given by 2j plus 1. So the higher the quantum number, the higher the energy, and the higher the degree of degeneracy. As we've mentioned a few times in class, spectroscopy is the study of the interaction of radiation and matter. And chemists use spectroscopy all the time to interrogate atoms and molecules to understand their structure and behavior. Rotational spectroscopy makes use of the quantum mechanical behavior of rotating systems. In particular, for our purposes here, we'll study rotational spectroscopy of diatomic molecules. These are uniquely connected to the rigid rotor model we've been studying because the rigid rotor tells us about the quantum mechanical states available to two-body rotating systems, just like a diatomic molecule. As it turns out, for reasons we'll understand later when we get to our study of spectroscopy near the end of the term, we learned that when a rotating system, in particular a diatomic molecule, absorbs radiation or energy to step through rotational quantum states, it is always the case that the change in the quantum number j is always equal to plus or minus 1. And so the amount of energy absorbed at any point in an absorption rotational spectroscopy experiment must be equal to the energy at state j plus 1 minus the energy at state j. If we expand out the definitions of energy in terms of j and the moment of inertia, we get the expression shown on the screen now. And after a little bit of algebra, what we find is that the change in energy is linear in the quantum number j. There's a constant h squared over 4 pi square I times j plus 1. Recalling that delta E equals h nu, we can now relate a change in rotational quantum state from, say, j to j plus 1 to a frequency of electromagnetic radiation that can cause that transition. A little bit of algebra brings us to the expressions on the screen now. And I'll note that in front of the j plus 1 term is a constant, h over 4 pi square I. Spectroscopists, for reasons we'll see in a minute, like to rewrite things so that that constant is rolled into this new term called the rotational constant, which is usually denoted by the capital letter B. And nu can be rewritten as 2 times b times j plus 1. It's also very often the case, as we see in infrared spectroscopy and in other kinds of spectroscopy, that the more natural or more common set of units to work in is wave numbers. Wave numbers are related to frequency by dividing by the speed of light, and we denote wave numbers as we have in the past with a tilde above the symbol for frequency. And so in wave numbers, the absorption frequency is equal to 2b tilde times j plus 1, and again the tilde over the b indicates that we mean the rotational constant in wave numbers now. And you'll note that the only difference between the b on the previous slide and b tilde is the speed of light c in the denominator. As with other kinds of spectroscopies you've seen, a rotational spectrum shows absorption as a function of frequency. On the top of the slide on the left, I've rewritten the relationship between the frequency absorbed and the transition we're observing. Again, this expression tells us the frequency required to move from state J to state J plus 1. And we recall from earlier that in rotational spectroscopy there is a selection rule that requires that the change in J is only ever equal to plus or minus 1. And in an absorption experiment, we're always stepping up. So what we'll worry about here is the transition again from J to state J plus 1. As we increase J states, the absorption frequency will naturally increase. But as the plot on the left here shows, the transition from J equals 0 to J equals 1, and the transition from J equals 1 to J equals 2, and the transition from J equals 2 to J equals 3, and J equals 3 to J equals 4, etc., all yield a set of lines that have equal spacing. And that spacing is equal to 2b. That doesn't mean that it takes the same amount of energy to move from state 1 to 2, or from 3 to 4. All that it says is that the energy required to go from state 0 to 1 is 2b energy units less than what's required to go from 1 to 2, which also happens to be 2b units of energy less than going from state 2 to 3, and so on. As a result, if we collect a rotational spectrum of our molecule, which initially will be in some number of initial J states, we'll get a set of lines in our spectrum, and just measuring the distance between those lines tells us about B. One final point to make here is that when rotational spectra are collected, it is the case that for molecules, absorption typically occurs in the microwave region of the electromagnetic spectrum. And that's why the terms rotational spectroscopy and microwave spectroscopy are often used interchangeably. So let's try an example problem to see how a rotational spectrum can be used to gain information about a molecule we're studying. The goal here, taken straight from your textbook, this is an example near the end of chapter 5, is to calculate the bond length of the molecule HCl. We're going to study a particular isotopologue, the one that has chlorine-35 isotope. And what we determine from the spectrum is that the lines in the spectrum are equally spaced by 6.26 times 10 to the 11 hertz. Again, that's a frequency that's within the microwave region of the electromagnetic spectrum. So let's turn and see how we could work through this problem to determine a bond length of this molecule. So the way we're going to attack this problem is to start by noting that the line separation in the rotational spectrum tells us the value of 2b. And using 2b, through the expressions we've derived earlier, we'll be able to compute the moment of inertia, and then using other expressions we have with the moment of inertia, we'll be able to back calculate the distance between the two centers in the diatomic. So from the problem setup, we have that the line separation, again equal to the value of 2 times the rotational constant b, is 6.26 times 10 to the 11 hertz, which is also equal to h on 4 pi squared times the moment of inertia I. We can rearrange terms and solve for the moment of inertia, and from the experimental spectrum determine that the moment of inertia is 2.68 times 10 to the negative 47 kilogram meter squares. Note that the moment of inertia is in units of mass times distance squared, in this case using SI units, kilogram meter squares. Now we'll recall that the moment of inertia is also equal to the reduced mass times the bond distance squared. So we'll now compute the reduced mass mu. Remember, that's equal to the product of the masses divided by the sum of the masses of the two atoms. And we'll use 1.01 AMU for the mass of hydrogen and 35 AMU for the mass of the chlorine-35 isotope. Now we have to remember to convert the reduced mass to kilograms, and so we use the conversion 1.661 times 10 to the minus 27 kilogram per AMU. Carrying out the computation, we find that the reduced mass is equal to 1.63 times 10 to the negative 27 kilograms. Now we can put numbers in where terms go in the expression I equals mu r square and solve for r. And we find that the bond distance, r, is equal to 1.28 times 10 to the minus 10 meters, which is equal to 1.28 angstroms. Summarizing what we've discussed in this video, we've seen that the rigid rotor provides a model for rotational spectroscopy, with delta J equal to plus or minus 1. We've used that selection rule to derive a series of expressions that predict how rotational spectral peaks can be related to a term called the rotational constant B. We then saw how a rotational spectrum can be used to measure separation between peaks to determine equilibrium bond lengths. And we noted that rotational spectroscopy tends to occur in the microwave region of the electromagnetic spectrum, and that's why, again, rotational spectroscopy is also referred to as microwave spectroscopy. That's it for now. Our next video is going to move into the next chapter of the book, Chapter 6, where we'll discuss the hydrogen atom. I hope everybody's doing well, staying safe and staying healthy, and I hope to see you all soon.